Activity 1.6 is similar to the previous activities in that we are tracking an individual's weight loss program. So this looks like we're following Fred's weight loss program over time. Again, the input would be the number of weeks, the output would be the weight, and it looks like they've plotted these points for us on the graph below. So the point 2, 195 would be reflected here, 4, 190 would be the second point, and so on. When you look at these points, you'll notice that they don't form a straight line, right? Some of the points are a little below where a line might fall or above where a line might fall. So we don't have a linear function, but we can still model the data with a linear function. The line that will go through most of these points is called the line of best fit, and the equation is called the regression equation. So the book has calculated that the equation of the line that will best fit all of these points is followed by this y equals negative 1.3x plus 196.7. So looking at this equation, we're asked what is the slope of the best fit line? Looks like the slope will be this negative 1.3. And then we're asked for the practical meaning of the slope. So the practical meaning is, well, Fred lost on average 1.3 pounds per week. We say he lost the weight because of the negative sign. If we had a positive sign, he would have gained 1.3 pounds per week. We're then asked for the y-intercept of the best line, or the best fit line. So here's our line. The y-intercept is the 196.7 or 196.7. I wrote the y-intercept as an ordered pair, and it says, what is the practical meaning of the y-intercept? Well, the y-intercept means the initial weight, or Fred's initial weight, is 196.7 pounds, right? Or Fred's starting weight is 196.7 pounds. So what I'd like to do is now actually draw a line through all of these points. We're going to draw the line of best fit. That's the fit that's going to go through as many points as possible. So if I were to actually graph this line on this graph, well, if you look on our next page, it would look something like this. Okay, and that negative 1.3 plus the 196.7, that equation describes this line that almost goes through all of our points. We can use this model to estimate Fred's weight at different times. So if we look, we see that we're asked, given an input, use the model to obtain an output. So the input is the number of weeks. So we're given week 9, and we're asked to find the output. So when I look at week 9, if I draw a line going up to my model and then over, you'll see it's 185 pounds. Right, again, I go to week 9, I go up to my model and I go to the left, and my output is 185. So for an input of 9, I get an output of 185. Next, we're told, given an output, use the model to obtain the input. When does Fred weight reach 185 pounds? So this time I go to the output, which is 185 pounds, and I trace a line to my model and then down to my input. And you can see, right, when I go from 185 to my model and down, I'm at 9 weeks. That's my input. So next we're told, all right, for week 4, Fred's actual weight is 190 pounds. So here's week 4. And if I travel up, you can see the dot here is an actual data point. So this dot represents his actual weight, which is 190 pounds. But the model gives me something different. Right? The model is telling me that Fred's weight is somewhere between 190 and 195. So the takeaway is our model is not a perfect predictor, but it gives us a close estimate when we don't have actual data.